Welcome. I'm standing between you and your break, so I'll try to make it as quick as possible. My name is Mike Sinclair. I'm in Hardware Devices Group at Microsoft Research, and I have some very highly skilled collaborators, Eyal, Mar, and Christian, not to say a lot of amazing interns that helped with some of the busy work and some of the not so busy work. And I'm going to talk to you about CapstanCrunch. For those of you who grew up here, it's close to a chocolate flavored cereal. But the real takeaway for the title is I want to develop a device that will simulate crushing of an empty soda can. Lots going on in there, nonlinear, linear, everything. This is kind of on its way to that. So the goal is to design a handheld VR/AR controller with natural haptic experience. Not that I have anything against things that buzz, but I think we should step out now and get into natural NUI haptics. Unfortunately, due to laws of nature, haptics are palm grounded for handheld devices. So we're stuck there. We gotta obey physical laws. Some of the ideal features we're looking for is the main haptic gestures that we'd like to render are for touch and grasp. Both touch and grasp with 1 to 4 fingers against the thumb or the palm. Engage at least the thumb and index finger, and eventually all fingers on one hand. Operate at human scale forces, roughly between a tenth and 15 to 20 newtons. Be fast. That's sometimes hard to do mechatronically. And low latency, at least less than 10 milliseconds. And coming from Microsoft, we'd really like to move that into product land. That's a hard thing to do these days, but in that respect, it needs to be low cost, simple, robust, i.e. hard to break, safe, don't want to squeeze little fingers, low electrical power for battery operation, and one size fits all. Categories of haptic devices, especially that will go in handheld devices. In the active sense, there's something inside the handheld device that produces a force that pushes against the fingers or the thumb. The pros of that, you have a motor of your choice plus gears if they're present, a position and maybe a force sensor, and a closed-loop, high-speed servo system. With that, you can synthesize almost any known or postulated behavior in haptics. It's great. You can do just about anything, especially if you put a force transducer as the end effector, in the end effector. And you get reasonable texture experience, albeit reduced quite a bit by a Z-axis wideband vibrotactile actuator like a voice coil actuator. The negatives, if they aren't obvious, is it requires a large actuator, usually motors and gears, one motor, many gears, for kinesthetic forces, which can be expensive, heavy, high power for limited battery life, may not be fast enough if there's a large inertial or gear load, especially if the gears are lubricated with viscous grease, compromised if abused. What happens when you step on the outside of this, besides the shell withstanding your force, this device that you're moving, will it break? And is it safe or not? Some of the brief history in our lab, just some of our previous haptic devices. There are more. Not slighting any interns in the audience who have helped on quite a few number of haptic actuators. In roughly 2013, we did Touch Mover. The user stepped forward, pushed on a robotic single-dimension screen, and the screen moved fore and aft according to your touch and according to the forces subjected during the application. A couple years later, we did Normal Touch, the little plate on the right with the detent on it. You put your index finger there, and as you approached a surface to touch, that device with 3 actuators met your finger and pushed against it when you actually were touching the surface, and the 3 actuators also tilted the little platform to replicate instantly the surface normal of the surface you were touching. gave you some idea about the contour, but no texture. There was also a force transducer in the end effector, so you can do compliance. You can actually simulate a squishy or a very rigid, stiff object. Oops. No. I'll go back. Pressed too many buttons there. Page 10. A little later, there was texture touch, which was a 4x4 pin array that replicated the rough surface texture of which you were you're touching with your finger. A little later was the claw, and this was a true high-end servo motor powered by a teensy controller and a PC plus a voice coil actuator for texture in the fingertip, and it could render pretty much any kind of known or postulated behavior, but it still had a fairly hefty motor in it. And those of you who are downstairs, we demonstrated torque, and in this case, no moving parts except the voice coil actuator. It's very hard to break, very stiff. It has a 2D touchpad under the thumb, so you can do micro manipulations between your thumb and two fingers, what you can't do with today's actuators. Resistive haptics, so that we're getting a little closer to the CapstanCrunch. The device offers resistance to the force that the user puts into the device. Passive haptics at the low end of the scale are essentially what today's controllers are. They're fixed shape. Whether it contributes to the actual haptic experience or not, that's to be determined, but the shape does not change. Obviously, it's low cost, it's the simplest, but there's very little natural interaction derived from that. Next is a programmable binary brake, either on or off, and that can be modulated when you're moving your finger against your thumb, and you either stop that movement or let it go. You can see some of the attributes there. You can program at finger distance or time when the finger should be stopped and when it should be let go. It requires a fairly simple brake and a position encoder to measure the distance between the finger and the thumb. It is not, excuse me. Why? And finally, programmable linear brake, which is what we try to do with CapstanCrunch. It's the best, we believe, of the resistance actuators. Can be high cost. I think CapstanCrunch, you'll see, lowers the cost quite a bit. Requires a position encoder, and you can buy some of these off the shelf. However, they're not used that much, and hence they're fairly expensive and not readily available. And they consist of piezo friction brakes, particle clutches, particle brakes. Many of you are familiar with those. And notice that in none of these resistive haptics is there any concept of energy storage, i.e. no compliance, no spring perception. And in the resistance actuation device, one of my many hobbies is sailing. And I have a resistance actuation device called a sailing winch. Many of you have been on a sailboat or other thing where you need to hold a very heavy force. There's a high tension side, low tension side. This has about a 1,000 to 1 mechanical gain. I hold with 1 pound of force on the low side. I can hold 2,000 or 3,000 pounds of tensile force on the other. But there's a high slip coefficient that goes along with that, a high static friction, low dynamic friction, and it's great for holding a high force, but when I want to lower that high force, I lower my holding force and it jerks, kind of unstable. And also there's a problem with overrides. You notice a single layer helix wound there. If you don't do it single layer, you may need a knife to get it off that winch. Capstan and rope basics. I'm taking advantage of an exponential input low tension with an output high tension, where the exponent is the mutual coefficient of friction between the rope and the capstan, and how many times around the capstan the rope is wound. You see the holding force that I'm holding or I'm controlling with a computer is small compared to the high load on the other side. When I want to lower the load, I reduce the T-hold force. So the T-hold force is the force that the computer is applying and supplying as a very low input force. The T-load is a high output holding force. And if T-hold is reduced to unbalance the equation, you reduce T-load enough, T-hold enough, T-load slips down, and the force in the equation is rebalanced, and everything stops. If there's little stick-slip difference, which is what we were looking for, so we can lower that load, reduce the load very smoothly, but the gain is reduced. But the compromise was acceptable. This is an inherently stable, reasonable open loop with a given T-hold. The output T-load is predictable. So I don't necessarily need a feedback sensor. It's unidirectional. That'll come later. It means that this operates in one dimension, one direction only. Some other nagging behaviors that I won't get into are the initial stretch of the rope and the funky friction and compliance of the rope yarn, which is put together with twist, the way yarn is, against the capstan surface. And I solved the override problem by milling grooves in the edge of my drum in order to keep the rope in check. So CapstanCrunch is based on a modified version of what I just showed you. I have a capstan that moves and a rope that doesn't move. The high end of the force end of the rope is grounded to my handheld device. The low tension side is hooked to a device that provides a predictable low force tension. There's very low stick slip between capstan and rope. Did many experiments to find, even consulting Celanese and Dow Chemical, they couldn't tell me. I was looking for something with a very low stick slip coefficient so I can move this load slowly and deliberately and smoothly. So I chose acetyl, which is Delrin capstan with the grooves milled in it, and Vectran rope. It's an LCD, much like the high-density polyethylene fishing line, but not quite as good as Vectran, which is a little more expensive, but it works great. There's low stick slip also compromise my mechanical gain quite a bit, but still a couple of 100 to 1. Programmable brake modulates stiffness only. Keep a note of that. I can only now have programmable stiffness in my closing of the finger. So for the internal actuator, I again call on ancient technology like the capstan rope is, and I call on what we today call the twisted string actuator. You notice there's a relaxed picture where the string is relaxed, and the wound tight version on the bottom. This is being actuated by a fairly inexpensive pager motor, and today's buzzing Haptics calls on these low-cost actuators as a low-mass armature. Again, keep my fingers away from this. Sorry. And they can accelerate and decelerate within a millisecond or two. They're great. They're very fast. They're very simple. They're more efficient than gears. They're back drivable. They're quiet. You don't get the buzz. Of course, what would be a robot without the zit, 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 zit? But these things produce no noise. This one you see here is equivalent to about a 20 to 1 gear ratio. Average power consumption fairly low. You don't need it 24/7. So through pulse width usage, you get a very low battery consumption. And the ones you see right there are slightly compromised. They're a little hairy, but they've undergone over 200,000 actuations. And here's a quick movie of it working and relaxing. Okay, now comes the final that we think is one of our contributions. We added compliance, a programmable onset of compliance, not a programmable compliance. So if you notice in the cartoon, the The brake capstan is shown below with the high tension side grounded, the low tension side you got your finger in and exercising kinesthetic force resistance. And between the two capstans there's a rotary spring. And if I engage the top capstan, used as a clutch, I try to open that spring. So I'm adding a constant spring force. Now, what the user tests have shown us is that people aren't gauging the compliant compression force against the release force. As long as you get some release force, the illusion is not broken. So this was a unexpected outcome of our study. So there's all of CapstanCrunch. Some of you witnessed it last night. We have a handle, a Velcro strap to keep the hand on the handle. You release it accidentally. Electronics, which is a teensy controller board with the 180 megahertz Cortex-4 ARM processor. A thimble, adjustable thimble. The length is fairly easily adjustable, so it'll accommodate many, many hand sizes. The brake capstan is the lower capstan along with its twisted string actuator, and the top capstan is for a clutch for engaging the spring and its respective twisted string actuator. So here's a quick part of the movie that's part of our published movie. And as you notice, the little actuators in the lower corner, you see them twisting and untwisting and whatnot. And you can simulate the stiffness of a hard object or a very soft compliant object. You can see the twisted string actuator engaging and disengaging. That's the brake. The one below it is for the spring. And you see the thumb. There's a static rest for the thumb, so you're exercising the force between your showing compliance between your index finger and your thumb. So user test, top level bit was something I just mentioned. We subjected the users to CapstanCrunch. We let them play with it, the variable onset of compliance as well as the variable stiffness by the brake actuator. And then we presented the users with three different devices. The CapstanCrunch, a device that looked the same but it had a real spring in it, so it had a fixed spring constant according to Hooke's law, and the claw, which is an active device that can simulate just about any kind of spring compliance. We were investigating the perception or not of compliance, and the results, again, the top level bits was that the CapstanCrunch did fairly well in high and low perception of spring compliance, whereas the claw had problems mainly because of low latency for doing low compliance, and the real spring obviously had one fixed compliance. It did great at its compliance, but if you tried to get the users to believe it was low or high compliance, they didn't believe it. So in the future, we want to reduce the size. You notice, especially the ones who played with it, saw that it was fairly large. We've already started reducing that by almost a factor of 5. We hope to get another 2 to 4 of them inside the handle so we can actuate all fingers. And battery and wireless operation are pretty much a no-brainer. So with that, thank you, and take questions.
Time for questions. Please put up your hand, state your name and affiliation. So you mentioned size at the end. Have you thought about scaling it up? So could you imagine doing this for full body experiences or to get cool feedback on an arm scale instead of a finger scale?
You need to visit our lab, and you'll see we have gone up the ladder a little bit. So we hope to take advantage of this fairly simple resistance braking device to actuate other kinds of limbs, or actually resist the actuation of other limbs.
If you try this with 4 fingers, if you do this with 4 fingers, how Do you have any worry about the different angles that your fingers want to move in versus a single plane?
Yeah, good questions. With the 26 or so muscles and joints you have in there, you got to choose a subset of that. So we already have a kind of a placebo in place. Doesn't do any actuations, but it's allowed. If you can imagine the handle and four little appurtenances, hinged appurtenances coming out of that with grooves in the top of them, kind of natural finger placement. Maybe with really, really small fingers, you might not be able to spread your fingers enough, but most people, they can get their fingers around that, and from then on, it's just the resistive force of those articulated finger plates that it does it. So that's where we're hoping to go next.
There's a question in the front.
I just have a simple question. Just curious what the mean time between failure of the strings. You're twisting it every time. What is expected life of twisting?
So the ones you saw there had already undergone 200,000 articulations, and so it's pretty good. What I'm using there is about $10 for 1,000 meters. It's common fishing line, and the fishing industry has turned to ultra-high molecular weight, high-density polyethylene, or Spectra or Dyneema, as are the trade names, very, very strong. Those little strings that you saw in there have a 200-pound test. It takes 200 pounds to break that. You don't do it with your hands. So I think that technology is already here, and it works great.
All right, let's thank Mike once more time.